Okay, last 5 problems from 2014. Here, a particle moves along the x-axis. Its acceleration is given by the graph above for all values of t between 0 and 1. At time 0, the velocity of the particle is negative 1/2. Which of the following statements must be true? Let's see. The particle passes through x equals 0 for some t between 0 and t1. Well, let's see. I think what I want to do here is a little bit of fundamental theorem. I know that the area, before I start looking at these, they're all about between time 0 and 1. That's what I'm noticing here. So if I set up a fundamental theorem expression here between 0 and 1, that's the antiderivative of acceleration is velocity. Right? And they did tell me this, right? So I know that the area under this, which I don't know exactly what the area is, but it's definitely, if I drew this triangle here, the area of this is 1/2. That's a 1 by 1 triangle. So the area here is definitely bigger than 1/2. This is definitely bigger than 1/2. This is greater than 1/2. And then here, plus another 1/2 from this. Right? So which of the statements must be true? The particle passes through x equals 0 for some time between 0 and time 1. So it starts with a velocity of 1/2, and it ends with a velocity of something that's greater than 1, right? Greater than 1/2 plus 1/2 is greater than 1. So that seems like it's got an awfully good chance of being true. Let's see what the other ones say. The velocity of the particle is 0 for some time between 0 and 1. Well, that seems to be true for sure, right? Because here it's negative 1/2 and here it's 1. So intermediate value theorem, it would have to be 0. And this isn't true because we don't know anything. We don't know anything about the position at all, right? We don't know where it is. They didn't say anything about that, so that's not true. It could be starting at position equals like 3,000 or something. That B looks awfully good. The velocity of the particle is negative for all values of t between 0. That's not true. The velocity of the particle is positive for all values. No. I mean, that's crazy because they told us, that seems like they told us basically that that's not true. Velocity of the particle is less than negative 1/2 for all values. No, definitely it's increasing. So B is the correct answer. So this, I think, was the way to go there. Fundamental theorem. How do you get from acceleration to velocity? Fundamental theorem. That's how. All right. Here's a function that's given by a derivative. What's the average rate of change of f over the interval from 0 to 3? All right, so how do we find the average rate of change of f? Well, f prime would just be, this is fundamental theorem too. If I take the derivative of this, I just get that, right? The x just drops in. I don't have to multiply by anything because that's just an x. So the average rate of change is the same as saying the average value of the rate of change. That's the average value of this from 0 to 3. So the average value of this. Remember that game? How to find the average value of a function? If I want the average of this, I take the integral of that from wherever to wherever and divide by how wide that is. So I'm going to do exactly that with my calculator. I'm going to find the integral. Let's clear that chunk out of there. Math 9 from 0 to 3. Square root of x cubed plus 2 dx, and I'm going to divide that by 3. 2.694. That's it. That's all there is to it. Number 90. Particle moves along a line so that its velocity is this for times greater than 0. For what value of t is the speed increasing? So that means speeding up. So that happens when, so the speed is increasing when velocity and acceleration are positive, or when they're both negative. So that's what I need to figure out here. I don't think I would try to take the derivative of that by hand, because that 2 to the negative t, you could probably do that without messing it up. But there's some things you might not remember, and I don't need to do it by hand. What I'm going to do is graph them both. So velocity is negative t cubed plus 2t squared plus, oops, that's not supposed to be up there. Try that again. Plus 2e squared plus 2 to the negative t. Alright, and now I need the derivative of that. That would be the acceleration. So I'm going to go, that's math 8. So I want the derivative of y1. And instead of putting a number here, I just wanted to do it for all x values. Give me the graph of that. And I'm going to look at my, it looks like I've got from, I know I don't need to go less than 0, so from 0 to, I could go from maybe 0 to 3. This is the largest number that's showing up here. So let's go from my window from 0 to 3. There's my velocity graph. And acceleration, I need them to be both positive or both negative. So it looks like there's 2 intervals. It looks like from here on, they're both negative, and from some small number here up to here, they're both positive. That might be, it looks awfully like this to me. I'm going to go ahead and check some of those values. So let's see. Where, sorry, I need to do that. Here, second, calculate the 0 of, let's find this one right here. I think that could probably seal the deal for us. So right here, yeah, that's 2.057. So that's the, this is the only answer here. So as long as you're confident that it's definitely all the values greater than this because they're both negative, V and A are both negative, so it's got to be this, and you can see that little spot that crosses. So you can check those if you want to, but that's definitely going to be the right answer. Right. There's one other, I'm just going to show you one other thing on this problem. There's one other way to do that without using the acceleration. I'll show you that. You could, instead of here, you could say, let's graph the absolute value of velocity is speed, right, if you're just in one dimension. So here I could math, let's see, my absolute value signs, absolute value of y1, and I'll just turn this off. and then graph that. So that's a graph of the speed. So if you want to know where it's speeding up, that's everywhere where this is increasing, right? And it's hard to see in this scale here, that little 0.17. I guess it's going down and then up in that little flat line area. But it's going up, and then it's going down, and then it's going up again. So that's another way you could look at that. Just look at a graph of the speed. All right, last two. Here, line L is tangent to the graph of y equals cosine x at this point. For what value of k does L pass through the origin? Okay, so line L, here's a graph of the cosine function. Line L is tangent to the graph at the point k comes, so it's just tangent at some point here. And we want to know for what value of k does that line pass through the origin. So you could imagine, this is how I would think about this. Here's all these tangent lines as you move along the cosine function. You can see none of them are passing through the origin until we get down here somewhere. So somewhere, and now that we kind of trace that, you can kind of see that somewhere down here there's going to be a tangent line that actually does just go through that origin there. So they want to know what's the k value where that happens. Well, that's kind of a special point because, or at least in this context, because the slope of this line, clearly it's negative. It goes through 0, 0, and it goes through this point here, as that k value is negative. But the slope of this, it's just y minus y over x minus x. So the slope of this is cosine k over k. If you're tempted to put a negative sign in front of that, don't, because the cosine of this value is going to be negative, so that'll take care of that. But I also know that the slope of the cosine graph at any point is just negative sine k, right? That's the derivative of this. So these two things have to be equal to each other. And that's back to a little graphing problem again. I just need to figure out where these are equal to each other. You could graph them separately and see where they intersect, or you could put everything on one side and see what the zeros are. It's up to you, whatever your preference is. I usually like to put it all on one side, but that's just my preference. You do it how you want. So, see where those are equal to each other. That's going to be where this is equal to 0. So, graph, I think that window there might actually be a good one. It looks like it might have just crossed there. I'm actually going to zoom in, and I'm going to make my, I'm going to go up to 4 there, and then I'd like to see a little closer to the y-axis. So instead of going from negative 10 to 10, I'm just going to go negative 1 to 1, because I just want to see where it crosses. Effectively zooming in on the y-axis there. So there it is. Somewhere between 2 and 3. Is that enough? Well, we've got 2. Looks like definitely, just eyeballing it, definitely closer to 3. But let's just check to make sure. 0, it's between 2 and 3. 2.798. There it is. And last one. The table above gives selected values of twice differentiable functions. We want to find the value of this. So the first thing I notice here is that this is a product. And the integration technique that I know that is most like the reverse product rule is integration by parts. So integration by parts in the abstract like this will work, and I can do like that tabular integration if I have something that's easy to take derivatives of and something else that's easy to take antiderivatives of. And this looks pretty good for that because this is derivative, so the antiderivative of this is g prime of x, and the antiderivative of that is g of x. Hopefully I don't have to go further than that. f prime of x, here I would take the derivative, but this says the f prime of x equals 3 for all values of x. And then if I take the derivative of that, I get 0. So, looks like I'm good here. So this technique is going to work here. So, it means the antiderivative of that thing is f of x times g prime of x minus, I don't know why I put a 0 there, sorry, minus 3 g of x. And this is a definite integral, we're evaluating that from 2 to 4. Okay, so let's see, so that'd be f of 4 times g prime of 4 minus 3 g of 4. That's what I get when I plug 4 in, minus f of 2 times g prime of 2 minus 3g of 2. Okay, so let's see if we can jam everything in here. F of 4 is 13. G prime of 4 is 7. Oh my goodness. Minus 3 times g of 4, which is 9. Looks like we actually have to do some math here. Oh, we have our calculator, don't we? So f of 2 is 7. G prime of 2 is 1. Minus 3 times g of 2 is 2. So 7 times 1 is 7. This is 1 here. And 13 times 7 is 91, last time I checked. And 3 times 7 is 27. So that's 64 minus 1 is 63. Ha! Did it without a calculator. All right.